All right, good morning, everyone.
Good morning.
Good morning.
Morning. All right, so it's Wednesday, and we are still working on 7.1. So today we're supposed to be starting 7.2, and we will get to 7.2. We'll see how far we get through it, but we do need to wrap up 7.1. These were some fundamental ideas, and last time I said that I would, you were only supposed to do the homework up through, I think, number 13. But I made a video for the homework solutions and I did the whole thing. So after I finish up 7.1, you should be able to handle the rest of it. All right. Any questions before I begin? Good. Okay, so we were talking about angles last time, and we determined that there are two ways to measure angles, either degrees or radians. And degrees are the more natural, I guess not natural, but most students come into a class like this and they've heard of degrees. Radians seem to be this mysterious thing, but I need everyone in here to really pay attention to radians, because as you move on in calculus, it's almost exclusively radians that we use. So I think I mentioned that last time. So even though there's a natural tendency to just say, oh, I'll just always convert my radians to degrees, we really want to become comfortable with the radian, the common radian angles. So here's a table that shows you a list of the common angles, the ones that you need to know. And I really don't like memorizing tables. So I have another way I want you to think about this, and we'll be using this throughout the rest of the semester. So it's very important that you understand what I'm about to show you. All right, so the way that I remember the common angles is this. I'm gonna first draw an X and Y axes. And remember, our standard position means that we're always going to start with the initial side of our angle is going to be pointed out the X direction, right? So that would be, that corresponds to the angle 0 degrees, which in radians, okay, so I'm going to do, in red, I'm going to do the degrees, and in blue, I'm going to do the radians. That would be 0 radians. Okay, now let's knock out the easy ones first. If we look at the angle that goes straight up, that angle is 90 degrees. And in radians, that would be pi over 2. Okay, so now here's where things are gonna be kind of important that you catch on to what I'm doing. What I'm gonna do now is, since this is 90 degrees, I'm gonna start counting around this, around and in positive direction. I'm going to be counting by 90s. So here I have 190, right? Everyone, I have 190. If I had two 90s, that would be 180. So that would put me here, right? That would be 90 times 2 is 180. Oops, in degree, in the red one, this would be 180. Okay, that's obvious, I think, to most people. 90 times 2 is 180. But with the radians, what I want you to think about is what would happen if you took this pi over 2 and you doubled it, right? What's 2 times pi over 2?
Pi.
Yeah, the 2's would cancel, right? And you would get just pi. So this is going to be pi radians. Now let's continue around the circle. I start here, I do 190, then 2 90s, 3 90s, 3 times 90 would be 270. But I've also done 3 of these pi over 2's. So if I look at that pi over 2 and I say, what's 3 of them? What's 3 times pi over 2? Then I cannot cancel anything here. So I just multiply the 3 across the top and I put 3 pi over 2. And that's it. I'm not going to make that like 1.5 or anything like that. I'm just going to leave this as 3 pi over 2. So again, started with pi over 2, and I'm counting 1, 2, 3 of them to get here. Are y'all following this process?
Yes.
Okay, now I'm going to go and do the fourth one. So I'm going to do 4 90s, right? 4 times 90, that would bring me all the way back around. This would be 360 degrees. So if I went all the way around, that's 360. But in radians, I would now have done 4 of these jumps by pi over 2. So 4 times pi over 2. And the 4 and the 2 reduce out, and I would just get 2 pi. So this would be 2 pi radians. Does that make sense? Any
Yes,
questions?
sir.
Yes? Okay,
Yeah,
good.
does this only apply in the positive or in the positive degree
Direction?
direction?
No, you could do it the other way too. So for example, let's say we wanted to know, I'll do it in different color. Let's say I wanted to know where -3 pi over 2 is. Okay, where's that angle? Well, first of all, it's in radians because there's no degree symbol. So I would look at this as -3 pi over 2's. And pi over 2 is 90 degrees. So what I'm doing is I'm going backwards or clockwise. 1, 2, 3. So this angle backwards, right, or clockwise, is the angle -3 pi over 2. Was that kind of your question, Joshua?
Yeah.
Okay.
I just wanted to make sure there wasn't any exception.
Nope. Okay, y'all good with this?
Oh, so if it's a negative, it would just have a negative sign with it if we went that way.
Yeah, and that would mean clockwise. If it's positive, then you go counterclockwise.
Okay, so everything's the same, you would just add the sign.
Yep. Okay, so with this idea, okay, with this concept, let's see if we can figure out where this would be. Where would 7 pi over 2 be? So again, this means we're going to count by pi over 2, and we're going to have 7 of them. Does that make sense? And we're going to go counterclockwise. So I'd start at my standard position. I go 1, 2, 3, 4, 5, 6, 7. So actually, this is 7 pi over 2 down here. Your angle is 7 pi over 2 is like a couple of rotations, but you would wind up pointing downward. Does that make sense? Any questions there? The main principle here is the idea of counting. Instead of looking at these angles as just like these random things, they're in some way like just multiples of one another. So let me move on. Let me continue. Okay, we've taken care of. I don't want to erase that. We've taken care of the axes. Oops. We've taken care of the axes. In other words, we've got any angles that lie on these axes, we've got a way to figure them out. The next important or common angles that we want to be familiar with, and I'm going to draw a whole new graph to do this, are the ones that are here, 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 and here. All right, so let's start with this first one right here. Now, we know that this straight up was 90 degrees, right? So shouldn't this be half of that? It's because I cut it like a perfect diagonal. So this should be 45 degrees. Now, in radians, this would be half of pi over 2, wouldn't it? Half of pi over 2. So the way you could write that is, okay, I'm going to take pi over 2. And I'm going to divide it by 2, which is the same as dividing by 2 over 1, which is the same as multiplying by the reciprocal. So this is pi over 4. I know that's probably more math than I needed to show, but I just want to make sure everyone understands that this is pi over 4. Okay, now, again, what I'm going to do to figure out all the other angles is start counting my way around. All right? And let's do all the degrees first. Okay? So when I do from here to here, that's 45, right? That's 145. Now I'm going to do 2 45s. That would give me 90 degrees. That corresponds to what we already knew that, right? We already knew that would be 90. Okay. And then I'm gonna go another 45 degrees. So I add 45 to 90. That would give me 135. And then I add a fourth 45, so 4 times 45, that would give me 180. And then I just keep doing this. Look, for degrees, it's easy because these numbers are easy. Okay, so you just keep adding 45 each time. So what do we got here? 225. This will be 270. Right? And then we add another 45. So what do we have? 315. And then we come back around. This would be 360. Oops, I forgot to put 0 here, 0 degrees. Do you all agree that the counting of the angles in degrees is fairly simple? You're just adding 45 in each case. It's the radian ones that get people. So let's try it with radians. So when I start out, I go from here to here. That's one of those, right? That's one of these pi over 4s. Now, when I make my second jump from here to here, I now have 2 of these pi over 4s. And do you all see that this 2 and the 4 reduce? Like they cancel out. This 2 becomes a 1, this 4 becomes a 2. And that means that the angle up here is pi over 2. Go with me? That corresponds to what we already knew. Okay, we knew that from the previous drawing, but things are matching up here. Now I make my third jump. So this is where it's going to get interesting. So this is my third pi over 4. Now, can you reduce anything here?
No.
No, so I'm just going to leave my answer as 3 pi over 4. Okay, that's this angle here. Now I have a fourth jump, right? My fourth jump, I now have 4 of those pi over 4s. And the 4s cancel.
So it
and
would
you
just
take
be pi.
Yeah, and that matches again with what we said here, right? We said it should be pi. So let's see. Let's call on some people here. How about Sierra? Sierra, you around?
Yes, I'm here.
Okay, Sierra, so what would be my next jump?
So it would be 5 pi over 4?
Yeah, 5 pi over 4. And you can't reduce that fraction, can you?
No.
No, so we'll just leave it as 5 pi over 4. Good. And then, let's see, Maddie, or Madeline, Maddie.
I'm here.
Yep, okay, so what would the next one be?
3 pi over 2.
Where are you getting 3 pi over 2 from? So
Well,
you're correct, but in terms of jumping, right, it's actually, how many pi over 4s have we jumped now?
6.
We've done 6, right? So it's actually 6 pi over 4s, but Maddie has already reduced that fraction for us. Do y'all see that? She said, okay, 2 goes in here 3 times, 2 goes in there twice. So it's actually 3 pi over 2. Yes? Good. Now, next one. Joshua,
Yes, sir.
where are we at? Radian wise here.
So that would be 7 pi over 4s.
Yep, that's 7 pi over 4s, and we can't reduce 7 pi over 4, right? We can't reduce the fraction, so this is just going to be 7 pi over 4. And finally, when we get all the way around, Cameron.
It would be 2 pi.
Yeah, so it's 8 pi over 4s though, right?
So
And
you
the 8 and the 4 reduce, okay? So what I'm trying to get you to see is that instead of trying to like memorize all this stuff, if you basically know how to count by pi over 4s, you can get all these angles. Does that make sense? As long as you can count by pi over 4, you're in business.
Thank you for showing us that way, because in high school we had to actually memorize the whole thing.
Yeah, and you know, some people are better at memorization. You know, like some people can like memorize a table and they're happy. And then if you're like me, I don't like that. I like to understand like something more like, I don't know, intuitive that I can, then it doesn't seem like just useless information in my head. Like I can build it myself, you know? So depending on how your brain works, you pick what works for you, okay? Okay, we're not done though, because we still need to take care of a couple of other common angles, all right? So the next common ones that we need to know, and I'll just make this real simple for us. Instead of counting by 45, we're going to count by 30 degrees. Okay, so what happens is you get 30 degrees. Ooh, that's terrible. You get 60 degrees, then you're going to be at 90, then here, then here. So basically we're taking each quadrant and cutting each quadrant into 3 equal pieces. Okay, so each quadrant has 3 equal pieces. So let's start with the angles. The angles are easy. 0 degree, I'm sorry, the degrees are easy. 30 degrees, 60 degrees, 90 degrees, 120, 150, 180. We're just counting by 30 as we go around. 210, 240, 270, 300, 330, and finally back around to 360. Okay. Now in radians, though, we need to figure out how we're going to go around here. All right. So we know that we should know already that all the way to the other side, 180 degrees is pi, right? And we have cut pi into 1, 2, 3, 4, 5, 6 equal sections. So 30 degrees should correspond to pi divided by 6. Does that make sense? Pi over 6 is just this whole straight line or straight angle cut into 6 equal pieces. And now we just start counting around, okay? This is one of them, all right? So Samuel, you there, Samuel?
Yes.
Okay, so Samuel, what would this one be in radians? So we've got 1 pi over 6 here, right? And now we're gonna have how many of them to get to here?
2.
2
2
of those pi over 6s, right? But what does that reduce to be?
To 1/3.
Yeah, exactly. So the 1 over there and then a 3 down here. So can we just write that as pi over 3?
Yes.
Yeah, okay. Understand?
I have a question.
Yes.
Where did you get the 6 from for the pi over 6?
Okay, because think about this right here, from here to here is pi. That's how we defined pi, basically. We said it's a half rotation. So because I've chosen to cut up the first quadrant into 3 equal angles, which means when you put the first and the second quadrants together, you should have 6 equal regions there. So that means we're taking the full this yellow angle, that yellow rotation, and we're cutting it into 6 equal pieces. So it's just whatever this is, which is pi, divided by 6. Another way you can look at it is, how did we get 30, right? Well, it's 180 divided by 6. If you take that and divide it by 6, you get 30.
Okay, I mean, that
All
makes
right?
sense. I didn't know pi was half a rotation.
Yes,
Makes sense.
pi is always going to be half of our rotation around. And 2 pi is all the way around, right? So pi takes you halfway, 2 pi takes you all the way back. Okay, so we have counted, we've done 1 pi over 6, 2 pi over 6, and then now, Michael. Are you there, Michael?
Yes.
Okay, so where are we at? In terms of counting, where are we at? How many pi over 6 do we have now?
3.
3 of them, so I'm gonna write that down. We have 3 pi over 6s, which really, if we reduce that, Michael, becomes what?
It would reduce to pi over 2.
Yep. Pi over 2. And that matches what we've been getting this whole time, right? So that's good news. Now we go again, we rotate again. You ready? Okay, so I'm just gonna open this up to everyone. So how many rotations have we done of pi over 6 now? This is our 4th one. So we do 4 times pi over 6. We can reduce that, right? 2 goes into both of those.
2 pi over 3.
2 pi over 3. Now we do our, where are we at? We're at our 5th rotation of pi over 6. So now we are at 5 pi over 6, which does not reduce, right? This is our 5 pi over 6. That doesn't reduce on, that's what I'm gonna write, 5 pi over 6. All right, let's try and speed this up. That's 5 pi, come here. All right, so that's 5 pi over 6. Here's 6 pi over 6. What's 6 pi over 6?
pi.
Pi, okay. The next one would be 7 pi over 6. Can you reduce that?
No.
No, 7 pi over 6. Okay. Next one is 8 pi over 6. That
Could be-
can be reduced, right?
4 pi over 3.
4 pi over 3. I'm just going to put here to the side. 8 pi over 6 is what this really was, but we reduced it. Now we're at 9 pi over 6. Then 10 pi over 6. Then 11 pi over 6. Then 12 pi over 6. Do you see what I'm doing? I mean, this is, just go back and reduce whichever of these you can reduce them. So this one reduces to be, let's see, 3 goes into there, 3 pi over 2. Here, this would be 2 goes into both of those, so 5 pi over 3. This doesn't reduce. That one reduces to be 2 pi. So let me just put little X's through the things that reduced. So that one reduced, that one reduced, that one reduced, and that one reduced. Okay, I hope that that helps because, again, for me, I mean, literally, I still do this to this day. Like, I don't even have these things like burned into my brain. I save my brain for other things. So if I want to know what this, like, if I'm sitting there and I'm like working on some problem and I have this angle right here, and I know it's one of the common angles, right? I'll just like real quick, I'll do it mentally. I won't do it on a piece of paper, but I'll just like real quick count my way around. You know, this is 1 pi over 6, 2, 3, 5, 6, 7, 8, 9, 10. That's 10 pi over 6. That's 5 pi over 3. Okay, so it's, yeah, all right. It is what it is. We move on. Any questions, comments, or anything else? Okay. All right. Now, continuing from last time, we have our common angles. You can memorize them from this or use what I just showed you. Now we want to talk about the area of a sector of a circle. All right, so think about a circle, okay? So you have a circle, you have a given radius, and you want to look at like a pizza slice from that circle. Make this a little bit bigger. So we're looking at this pizza slice here. So if you know this is your radius, please note that this side would also be your radius from here to that point. Then if you know the radius, okay, so you have to know what the radius is. And if you know the angle, then you can find the area of this pizza slice. So the area is the amount of, I guess, what it would take to paint that little piece, right? The area is going to be equal to 1/2 the radius squared times theta. Now theta, we haven't really talked too much about this. Theta, just so everyone knows, that is the Greek letter theta. So when I say theta, I'm referring to that symbol. Think of theta as like the variable x. It's just we like to use Greek letters for angles. That's just something we like to do. Well, someone did it, I didn't do it. But whenever you see Greek letters, they usually represent angles. We'll use theta, we'll use beta, we'll use alpha. Those are the most common Greek letters that we'll use to represent angles in this class, right? So this is just saying if you want to know the area, you take 1/2 of the radius squared times the angle theta. Now, I'm not here to prove that formula to you, okay? You just have to take that formula on faith. If you wanted to prove this formula is true, you take Cal 2 and then Cal 2 will prove that's true, all right? But not here. So there's a big catch to this formula, and I don't want you to make a mistake here. There is a huge thing you have to remember. Because when we measure angles, you can do degrees or radians. You have to know that when you use this formula, your angle must be in radians. If your angle is in degrees, you can still use the formula, but you have to convert from degrees to radians before you use the formula. So we're about to do an example and you'll see what I mean here. So the example says, find the area of the sector of a circle of radius 2 feet formed by an angle of 30 degrees. So we basically have a circle, we have a radius of 2 feet, and then we're going to have an angle that is 30 degrees here. And that creates our little sector we're trying to find the area of. Okay. So we can use the formula, but our angle 30 must be converted. So the first thing I'm gonna do is convert 30 degrees over to radians. And we did that last class, didn't we? So all you do is take this 30 degrees and you multiply it by, anyone remember?
180 over pi.
What is that?
Pi over 180.
Pi over 180. So the way I remember this is that I'm either going to use pi over 180 or I'm going to use 180 over pi. It depends on which way I'm converting. I always remember it because if I have degrees here, I want the degrees to go away, then I need the degrees on the bottom here. So this should cancel out. So let's see. Well, 30 goes into 31
Pi over
times.
6.
30 goes in there 6 times. So that's pi over 6, isn't it? Now we need a decimal because we're going to use a formula. So I'm going to get on my calculator. I'm going to do pi divided by 6. That's approximately 0.52359. Yeah, that's good enough.
Wouldn't it be better to leave it as pi over 6 and then find the decimal at the very end?
That's kind of a, you're still going to have error. As soon as you go to a decimal, you're going to have some error, right? So it just depends on where you want the error to occur. If we do it here, if we round here, then we're still going to have error because it's just theta and it's not like theta squared. Our error would be the same no matter where we do it. Now, if this up here were theta squared, then it would be better to leave it as pi. But see, not everybody has a pi key on their calculator. That's why at some point we have to round, right? Pi is irrational. There's no way to write the number out. So in the real world, we don't have to worry about, rounding is a huge deal. Don't get me wrong, rounding is a huge deal. But if you go far enough out, the error that you have is so insignificant that it doesn't impact your ability to like manufacture something. Think about it like, I know some of you are like engineering majors. Think about if your company manufactures ball bearings, right? Ball bearings. You have limitations on how precise you, like how perfectly spherical you can make a ball. I mean, there's restrictions on how, what's the word I'm looking for? There's going to be problems in your sphere. Like it's not going to be a perfect sphere. It's impossible to construct a perfect sphere. So your ball is going to be a little bit off. There's going to be error, but the amount of error is what's important. So if you're making ball bearings for, let's say, a tricycle for a kid to play on, your bearings can suck. I mean, they can be really, really poorly made and the kid's still going to be able to ride the tricycle. But you can't use those bearings in an aircraft engine, right? Because then it would fail. So every sort of manufacturing process has error in it. It's just what tolerances are acceptable. So I'm going off on a tangent here, Maddie, I'm sorry, but error for us is not something we're going to focus too much attention on. You know, it's like round, go a couple of decimal places and let's move on. All right, so here we go. Let's go to the formula. So I'm going to do area equals 1/2 the radius, which was 2 feet. So I'm going to put 2 squared times the number I just got, 0.523. Someone already got this for me. So what's the final answer here?
1.0471 square feet.
Okay, so I'm going to just put that. Do I have anyone who agrees with that? Yes, thumbs up.
Yes.
Okay. So now the question is, what's the units? And I heard feet squared. That is correct. Remember that the original radius was given in feet. And since we're talking about area, we have to take the unit and square it. So there it is. All right, any questions? It said to round to 2 decimal places here. So we would actually round this to 1.05 square feet if we want this answer, right? Any questions there? So it's just a formula you plug in. Just remember, you've got to have it in radians, or else you can't use the formula, right? The angle must be in radians. All right, now we're going to talk about something: linear and angular speed of an object traveling in circular motion. So look, let's just talk real quickly about what we know already about speed, okay, about velocity. So if you're, let's say you're a person and you're going to run. Can you tell they're running? That's pretty awesome, huh? You can tell that I've been drawing stick people for a long time, right? It's pretty impressive. So if you can't draw a stick person that well, don't feel bad, all right? I'll even put a little hat on. Check that out. Okay, so here we go. If you're running, right, in a straight line, you go from point A to point B, right? That's a distance that you travel, right? So you travel some distance, and it takes you some amount of time to do that, right? So your speed or velocity, I'll put V, would be the distance you travel divided by the time it takes you to travel it. So let's say that you ran, I don't know, let's just say that this distance was 50 feet. And let's say you ran that distance in 5 seconds. Then your velocity would be the 50 feet divided by 5 seconds, which means that you were traveling 10 feet every second on average. Okay, so this is an average speed, 10 feet per second. So velocity is distance over time. Everyone agree with that, or comfortable with that idea? What we're interested in is talking about the speed of an object that's traveling around a circle. So I put together real quickly a little animation for you right before class. I barely got this done. Okay, so okay, so here we go. Take this back to the beginning. So let's say you have an object that's on a circle and it's traveling around that circle, okay? So what we want to know is, can we actually define the speed of that? The problem is it's not straight line motion, right? If it's a straight line, like a person running in a straight line, then you can easily calculate the distance because it's just a straight line, right? But here, because the object is traveling along a curve, we need some way of trying to figure out how far they ran. Does that make sense? Like, how far did they actually run? Well, we're going to have we're going to need some formulas to do this. Also, I want to point out something else. I know it's hard to see it here, but not only is the object's position changing, right? It's changing at a certain rate, right? And I can slow this down, right? So you can have someone who's, you know, the object's going a little slower, right? Or you can speed it up. Notice that if we measure the angle, that not only is the object's position changing, or not only does the object have a speed around the circle, would you agree that the angle is changing? And so there's a rate at which the angle changes. Like right now, do you all agree that this angle is changing pretty slowly? Right?
Yes, I would say
It's,
so.
it's kind of slow. Now let me speed this person up. Okay, here we go. So now that angle is changing very fast, right? The angle is, and the object is moving very fast. So we have two concepts here. We have the concept of the speed of the object itself, and then the speed of the angle. They're two different things. So we have what's called linear speed, which is a weird name for this because linear speed is the speed of the red dot. Even though it's not traveling in a straight line, we call it linear speed. And then we have something else called angular speed, which is the rate of change of the angle. So two different concepts. All right, so here we go. So to do this, to be able to do any of this, I have to give you a single formula. It's a very important formula, and I didn't put it on here because I wanted to make sure I really stressed it to you. It's what's called the arc length formula. For a circle, okay? You can have arc lengths of other things, but for a circle, we have a very, very nice formula that everyone here should, I'm not going to say memorize, but you should know it. Okay, so let's say we have a circle, and let's say we start at the center, we go out to any point, and then we travel through some angle. I'm going to call this theta. We already have a formula to calculate the area of that sector, right? The pizza slice. But I'm interested in knowing if we can somehow measure this arc. Find the length of that arc. Arc length, right? Find the length of that arc. So I'm going to call this S. There is a formula, and the formula is really nice. Oh, I forgot to label the radius. The radius is on here. The formula is this. S is equal to R times theta. That's it right there. Such a simple formula. But there's, again, a very big catch here. This theta must be in radians.
But-
So go ahead.
Yes, sir. So so the hardest part for us is probably going to be the conversion, but once we have it, it's just an easy plug in to
Yeah,
that.
just a plug in. I think the harder part's going to be, these are going to be word problems. So it's going to be you trying to figure out how to convert the word problem into the math. Once you know how to get to the math, it's simple multiplication, division type stuff. Okay. Now, this may seem like a very strange formula, but it is consistent with what some of you already know coming into this class. Like at the beginning of this class, I may have asked, I could have asked you, hey, if I have a circle of radius, let's say R, and I asked you for the circumference of that, that's the distance around it, right? All the way around. Can somebody tell me? You learned it like in the past. Does someone know what the circumference of a circle is?
Isn't
pi r
it 2
squared.
pi r?
Pi r squared is the area of the circle.
Isn't
2
it 2
pi
pi
r.
r?
2 pi r. 2 pi r is the circumference of a circle. You can look this up on the formula sheets. By the way, did y'all see I posted the calculus formula sheets? Did y'all see that in Canvas? Oh, come on, I had to have. I'm going to check it this time.
I didn't see it, but you
Didn't
could
see
have
it?
posted it.
I swear I did it. I'm
Well,
gonna
I
go.
mean, you probably posted it. It just doesn't alert us.
Yeah, it doesn't alert you. It won't alert you. But let me just double check. Oh, man. So if you go to our course, you go to files. What? All right, I'm doing it right now. This is ridiculous. That's why. Y'all just hang tight. Think about your favorite movie right now or something.
Sir, I have
Yeah.
a question.
Yeah,
It's
go
a
ahead.
little off topic, but since Super Bowl is this weekend, who do you think's gonna win?
Who do I think's going to win? The Chiefs. But who do I want to win? I want the Bucks to win.
Yeah, same here.
But I always like to see a good game, but okay, I'm gonna look. If I don't add this file later on today, then everyone's gonna get like a 5-point curve on their test. Okay, so I know y'all want me to forget now, but I won't now. I will have that in there. So in that formula sheet, when you get it, here's what it'll have in it. Okay, it'll have, well, it even has this formula right there in here, but you go up to a circle, circumference is 2 pi r. Okay, circumference is 2 pi r. So back to this. This should make sense now, but this formula is actually a general formula for this. Because if you look at a circle and you want to know the circumference, that means you're starting here and you're going all the way around, right? All the way around, that's your S. So what's the angle going all the way around? If you go all the way, what's that angle in radians?
2 pi.
2 pi. So what would happen if you replace that theta with 2 pi? You get 2 pi r, right? So this is a more general formula for finding you can find the distance all the way around, which would be the circumference, or you can just find a little piece of it. Just, it's up to you. All right, back to what I was talking about here. Where is it? Okay, so back to this speed stuff. So the linear speed, suppose that an object moves on a circle with a radius r at a constant speed. If s is the distance traveled in time t on this circle, then the linear speed v is just s over t. All that means is we're going to take the measurement here, whatever this arc is, that'll be like over here on the right side, that'll be like this distance from A to B that the person ran. So we have to use the formula for that. So when we look at that formula, it's S divided by T. S is really R times theta. Do you all agree with that? Because that was the formula I just gave you for S, R times theta. So if you want to know the linear speed of an object moving around a circle, you just need to figure out what the radius is. You need to tell me what angle it moved through and how long it took for that to happen. All right. Now the angular speed, and remember the picture I showed you, this yellow thing was changing, right? There's a definition for that. The angular speed, which we use a Greek lowercase letter omega of an object, is the angle measured in radians swept out divided by the time it takes to sweep out that angle. So just know these formulas. We're going to use them in an example in a moment. But do y'all see that this over t is actually this right here? Do y'all see that right there in this formula? Theta over t is here. So we could replace this with omega if we wanted to. And that's what this final formula says. If you just take this velocity and replace this theta over t with omega, then you get r omega. Don't worry about it, just write them down. Let's do an example. All right, here we go. A child is spinning a rock at the end of a 2-foot rope at the rate of 180 revolutions per minute. This does not sound like a good situation here for this kid. So the question is, find the linear speed of the rock when it is released. So this kid's sitting there spinning a rock on a rope. I don't know why they're doing that, but they are. And then they're going to let it go. And the question is, how fast is that thing going to be coming out, right? So let's draw a picture. Let's just imagine the rock is moving along, right? It's moving along. Let's say they didn't tell us which way it's traveling, but let's just assume it's traveling in this direction, going around, right? Now we know that the velocity is equal to s over t, right? All we're given though is the radius. We know that the distance from here to here is going to be 2 foot. All right. So we have that formula. Let me write the other formula we have. Omega is equal to theta over t. And then the other formula we have is that V is equal to R omega. Those are the three formulas we have to work with. And we are trying to find, what are we trying to find? Linear speed? So that's V, right? We're trying to find V. So we can either use this formula or this formula. So what do y'all think? Do we know the radius?
Yes.
Yes.
Okay.
So we
So
would use the V equals.
We do know this, right? We do know that, check. So do we know omega? Do we know omega? Well, do we know, so omega is theta over time. Theta is the angle we pass through in some given amount of time, or omega is the angle we pass through in some given amount of time. Do we know that?
Yeah.
180
182 pies in 1 minute.
We do 180 revolutions in 1 minute. Let me write that down. We do 180 revolutions in 1 minute. This is an omega because, well, kind of. 180 revolutions is not in radians. See, we need this in radians in order to use the formula. So what is 1 revolution? How much is that in radians?
2 pi.
2 pi.
Pi, right? So what we need to do is convert this over. We need to take 180, multiply that times 2 pi, and then divide by 1 minute. So what we get here is what, 360 pi? I'm going to put radians even though I don't need to. Radians, it's implied. If you just write the number without anything, it's implied per 1 minute. This is an angle. Do y'all agree that's theta? 360 pi radians, that's an angle. That's the angle we turn through. And we do that in 1 minute. That's our time. So this is omega. So all we have to do now to get velocity is take that formula V and take our radius. Oh, let me write down our omega, and then take our radius, which is 2 feet, and multiply that times 360 pi. I'm not going to write the radians over 1 minute. And then just multiply straight across. So I'm going to actually multiply this out and do 2 times 360 times pi. And then, yeah, that's it. So I get approximately 2261.9. I'm going to round 2 decimal places, 0.95. And then what are my units? Because this is a speed, this is a velocity. What units were still here?
Radians per minute.
It would just be minutes, right? Because it follows.
What units were still there? I still had the 2 feet, right?
Oh, so it would be feet dash minutes or minutes.
Per minute, or feet over minutes. The radians is not there. Remember, I don't write the radians. That's why radians are so nice to use. Is it's what we call is like a unitless measurement. You don't have to put the unit there. So you have 2,261.95 feet per minute is the linear speed of that rock. So any questions on that? Is that fast? Is that fast?
No, that doesn't seem to make sense. Like if you really think about it happening in real life, it doesn't really make sense.
It doesn't what? Make sense?
Yeah.
What, well, do you think that number's too big or what?
I think it is.
Okay, so let's see if it is. Most of us, the thing that most of us are most comfortable with is miles per hour, right? Like right now, if I tell you, would it hurt if you hit a brick wall at 2,600 or 2,261 feet per minute? Would that hurt you? Would that kill you? Most people would be like, I don't know, you know, like
it's gonna hurt regardless.
miles per hour, though, it's pretty easy for us to understand, right? So let's convert this. This is feet per 1 minute, and this is an exercise in conversions. All right, if I want to convert feet per minute into miles per hour, the first thing I have to do is get rid of the feet. So I need to know how many feet there are in a mile. So I put feet down here and I put mile up here. Does anyone know how many feet there are in a mile? No?
5,280.
5,280. That's not something that you need to know, but seems like every time I've ever taught this class, someone in the class knows what the conversion is. It's 5,280 feet in 1 mile. So if we do that, the feet will cancel. Then I need minutes to convert to hours. So that means I need minutes on top and hours on the bottom. So how many minutes are there in an hour? 60, right? 60 minutes in 1 hour. So now just multiply all your numbers across, the minutes are gone. So multiply all your numbers across the top and then divide by 5280. So 2261.95 times 60 divided by approximately 25.7 miles per hour, mph. You see what I'm saying? Like, if I would have told you, hey, you're running along at 2,261 feet per minute and you hit a brick wall, are you dead? You know, like that's hard to comprehend what that is. But you convert that into miles per hour, it's a little bit easier to understand, I think. 25 miles an hour, 26 miles per hour. Yeah, I think you'd probably be pretty hurt though if you hit a brick wall at about 25 miles an hour. Okay, we are moving on. Can I move on? We need to get out of this section. All right, we will have more practice with this later. All right, we are now going to talk about right triangle trigonometry. So there's a lot of definitions in here. There's a lot of language. Don't get so bogged down on trying to copy all this down. Remember, I will send you all these notes. So first thing, we just need to all understand some language I'm going to be using in terms of right triangle. So first of all, a triangle is three sides, right? Three sides to a triangle. A right triangle is a triangle that has one of its angles is 90 degrees. Okay. And we usually put a little box or a little like partial square right here on that corner to show it's 90 degrees. Now, whenever you do this and you have a right triangle, you'll have two short sides and one long side. The two short sides are called the legs, and then the long side's called the hypotenuse. Now, an acute angle is any angle theta that is between 0 and 90 degrees. All right, so this is a definition of what an acute angle, and I think we did talk about this last time, but now we've defined it for sure. An acute angle is an angle where the measurement of the angle is between 0 and 90 degrees, or if you want to use radians, between 0 and pi over 2. Anytime that you have a right triangle, do you all agree that the angle here, theta, and if I put another angle in here, let's call it beta, do you all agree that both of those angles must be acute angles? Why?
Because the sums of the angles of a triangle has to equal 180 degrees. So if they weren't acute, then it wouldn't be a triangle.
Exactly. So well, some of us know, some of us may not, that if you have any triangle, it doesn't have to be a right triangle, any triangle, that if you take all the angles, let's call this angle A, B, and C, the sum of the angles must equal 180 degrees for any triangle. So if I tell you that one of these is 90, right? If one of those is 90, and now I subtract 90 on both sides, A plus B would then have to be 90. So neither one of these can be 90. They both have to be less than 90, because if let's say A is 90, then B would have to be 0, and then you wouldn't have a triangle because you would have an angle of 0. So the restriction is that these two angles must add up to be 90, which means each of them has to be between 0 and 90. That makes sense? Yes. By the way, this fact that the sum of the angles of a triangle has to be at 180 is not always true. I know you've been told it's always true, but it's not, and I'll show you an example. So let's imagine that when we're talking about triangles, we're always talking about triangles on a flat sheet of paper, right? Flat sheet of paper. But let's imagine that we don't live on a flat sheet of paper. Let's imagine we live on a sphere like the Earth. Okay? Then imagine drawing a triangle on the Earth. And I'm going to draw a very simple one for you. I'm going to start at the North Pole, and I'm going to follow a straight line down to the equator. Now, when I say straight line, that means I'm going to walk along the Earth down to the equator. It would appear to be a straight line, but in reality, it's curved. Do y'all agree? Like that? Now, let me pick another point on the equator, like here, and let me connect those with, well, what would be straight on the Earth, or what would appear straight would be a line like that. And then let me go back up to the North Pole with a straight line up, okay? So it's almost like I'm moving along the like latitude and longitude lines of the sphere. On a sphere, that is a triangle. That's what a triangle looks like on a sphere. So we call that a spherical triangle. If you look at the angles for this triangle, this right here, this angle here is 90 degrees. And this angle here is also 90 degrees. And so right now, right here at this point, we already have a triangle that has angles that add up to be more than 180. Because you still have to add this angle in here, whatever that is, we'll call it theta. So definitely adds up to be more than 180. So my point is, like if if it's a trivia question, the sum of all the angles of a triangle have to be 180. The answer to that would be false, because it depends on where you live. It depends on the space you're in. If you're on a flat sheet of paper using standard Euclidean geometry, I agree. But if you're somewhere else, it doesn't have to apply. So I guess the big moral of the story is this. All the math that you've done in your life, you've been a fish in a fishbowl, okay? Those are fish in a fishbowl. I know you know that. You can tell by the drawing how good it is. Those are fish in a fishbowl, okay? All the math that you've dealt with your whole life is because you live in a fishbowl, okay? You've done everything on a flat sheet of paper. I'm here to tell you that there's an entire universe of stuff outside the fishbowl that you're completely unaware of, where math plays a role. So like these fish are pretty unaware of the dog that lives in the backyard, right? But there is a dog in the backyard. So this is called spherical geometry. And that's a whole different field of math, spherical. We like to work in spherical geometry. Why do you think we like spherical geometry? We live on a sphere, right? Roughly. A lot of things in the universe are spherical. So we have whole different systems. We have whole different mathematical systems where we have different rules. I'll give you one more. I'm sorry, I'm going off on a tangent. And this is, I try not to do this too much. Let me give you one more example. Two parallel lines. What is the main property of two lines that are parallel? If I told you to tell me a little bit, you're explaining it to like a third, fourth grader. What are two parallel lines? What are you going to tell them?
They're never going to touch.
They're never intersect.
I totally agree with you. I totally agree with you. So I'm gonna show you two examples of that. First example on the left, I'm gonna draw a picture. And then I'll tell you what it is. That's a street. And those are some buildings on the side of the street. And we're looking from the top down, right? Can you all see that, like the street, these are parallel lines? In the middle, the little dashes in the middle of the street are parallel. So these aren't ever going to hit each other. In fact, these edges of the building are parallel, so they're not going to hit each other. So that's a decent drawing, right? Decent. And I'm following all the Euclidean rules of geometry. Now I'm going to draw you the same picture using something else. So those of you who've taken any sort of drawing class will recognize what I just drew as a vanishing point. And then here come my buildings. I'm doing this real fast to try and get through this bit. So there's another drawing of the same exact thing, but now I'm actually making it look more like a real life situation, aren't I? I'm tricking your eyeballs into thinking that this is three-dimensional, even though it's not, right? But to trick you, I had to break the fundamental rule of Euclidean geometry. And that is, I had to make parallel lines intersect, right? In reality, these would be parallel lines, but on the picture, it's not parallel. So this is actually called perspective geometry. And the rules here are different than the rules here. So again, the fishbowl is Euclidean geometry. The perspective geometry is non-Euclidean. So I'm not trying to make you feel like you don't know anything, but I'm just trying to get you to see that there's all this other stuff out there, okay? There's all these other things that we have that allow us to do the things that we do in this world. All right, we're moving on. I need to shut up. Okay, now let's talk about similar triangles. So similar triangles are are basically two triangles that have the same angles in them. So I drew you two triangles here. These are different sized triangles, but they have the same angles. They both have a right angle. They both have theta. So I'm telling you these angles are the same. And if those two angles are the same, then whatever this angle is up here, I'm going to call it beta. That must also be beta. These two triangles are called similar. And similar means that all corresponding ratios must be equal. So that means that if you take any two corresponding sides, so if I take C prime, or that's C prime with the little dash on it, and C, if I create a ratio out of those, that must be equal to any other corresponding ratio. So now let me take A prime over A. If I make that ratio A prime over A, those must be equal. That's the property of similar triangles. If you take corresponding ratios, they must always be the same. Now, this is important because of the next thing, the next definition. We'll use this more later. Don't get too bogged down on it. So now we finally introduce the trig functions. So pre-cal is about a lot of things, but one of the main ideas is the 6 basic trigonometric functions. From this point forward, these are going to be present in all your math classes, all right? These 6 basic trig functions. And we have to define what they are, right? So there's actually, we're going to define them 2 different ways in this class. The first way we define them is by using triangles, and that's what today is about. And then later on, we're going to use something different to define them. But for now, we're going to call these the trigonometric functions of acute angles. So it's very important that we're talking about acute angles right now. So focus your attention on that triangle over there on the right side. And we're looking at this angle theta here. All right. We are defining now the 6 trig functions. The first function we're defining is called sine of theta. That's what's called sine, S-I-N-E of theta. The way we write that is sin theta. You might see it written this way, sin with the parentheses theta. And you may ask yourself, well, what is it, right? What is sine of theta? Well, I'm telling you right now what it is. It's the B on the triangle divided by the C. So it's just a ratio. It's just this side divided by this side. Okay, so sine of theta is always going to be B over C. And then we have the other 5. And I'm not going to go through each one of these. I'm just going to go through their names. The next one is cosine of theta. That's the way we write it. And it's A over C. Tangent theta, written tan theta, is B over A. And then we have what are called the reciprocal ones, but we'll get to that in a minute. Cosecant theta, which is written CSC theta, is C over B. Do y'all see that these are just flipped? Instead of B over C, this one's C over B. And then secant theta is C over A, so it's just that one flipped. And then cotangent of theta, written this way, is A over B, which is just that one flipped. So that's the way we define the 6 trig functions of acute angles. And there's another way to remember them, because you can memorize that, but it's kind of like, if you don't like memorizing, then it's not easy. So there's another way, and this is the way I prefer of remembering all of this. If you have a triangle, instead of looking at it as like A, B, C, we can call the side, here's theta, we can call the side that's closest to theta, okay, this leg, we can call it the adjacent side, adjacent. The side over here, this side here, we call it the opposite of theta because it's over here opposite of theta. And then the hypotenuse is just the longest side. If we define it this way, or if we use this notation or labeling instead of ABC like this, then sine of theta is opposite over hypotenuse. It's this opposite side divided by this. Cosine theta is the adjacent divided by this hypotenuse, and so on and so forth. Again, not something you want to try and memorize. So we have this cute little It's not, I don't think it's an acronym. I've had this debate with my students before. What's an acronym? Like an acronym like NASA, right? Is that an acronym? NASA? FBI, is that an acronym? MAD, Mothers Against Drunk Driving, is that an acronym? So this is open to debate. Does an acronym have to actually be like an actual word? Like FBI is not a word, but is it still an acronym? I don't know. I'm not an English major.
It doesn't have to be an actual word.
Doesn't have to be? Okay. Well, then this is an acronym. SOHCAHTOA. Have y'all heard this before? Anyone? Shake your head.
No.
Yes.
So many times.
Yeah.
SOHCAHTOA, good. So SOHCAHTOA was a Native American young girl who discovered trigonometry. Her name was SOHCAHTOA. So I'm just kidding. She's not a Native American. It has nothing to do with Native American, but it sounds kind of like a way you can remember it. All right. SOHCAHTOA. So all this is a cute way of remembering this right here. Sine, this is really sine, is opposite over hypotenuse. See how that works? Sine is opposite over hypotenuse. The next one is cosine is adjacent over hypotenuse. And then tangent is opposite over adjacent. That's exactly these three, right? Do y'all see that? Now the other three, cosecant, secant, and cotangent, you just have to remember are these flipped over. So you have to know that cosecant goes with sine. You need to know that cosine and secant go together, and then you need to know that tangent and cotangent go together. Let's do some problems. We can sit here and look at formulas all day long. Let's do some problems. All right. So here's a triangle. Let's find all 6 trig function values of theta. So I'm gonna just make sure you understand theta's here, which means the opposite side is this side, the adjacent side is this side, and the hypotenuse is this side. I'm going to jot down SOHCAHTOA just to have it. And I'm going to start with sine. Okay, what is sine of theta? Well, that should be the opposite over hypotenuse, right? What's the problem though?
You don't have the opposite.
We don't have the opposite side. We don't have the opposite side. So we can't figure out what sine of theta is. So now what you have to do is go back to something that you should, again, know coming in here about right triangles. Does anyone know what I'm about to say?
A squared plus B squared equals C squared.
Yeah, so if you are given any right triangle, call this side A, B, and C, or those sides A, B, and C, then we have the Pythagorean Theorem that says A squared plus B squared must equal C squared.
You could
So
also
that.
just use cosine theta, right?
Pardon me?
You could also just use cosine theta, right?
What do you mean?
To figure it out.
Our best bet's probably going to be the Pythagorean theorem because
Okay.
they
Well,
already give 2 points,
Cosine
right?
theta, we can use, we can figure out what cosine theta is because it's adjacent over hypotenuse. I agree with that.
Yeah, that's what I was asking.
But how do you do that? How can you use that to get sine theta? I guess that's my question. That would be my question back to you,
Oh, okay.
right? So right now we're trying to find all 6 trig function values. So we want to know what cosine theta is. We want to know what tangent theta is. We want to know what cosecant theta is. We want to know what secant theta is. And we want to know what cotangent theta is. We want to know what all of these are.
Okay.
So to find sine, I've got to know the opposite and the hypotenuse, but I don't know the opposite. So going back to this Pythagorean, if I know that A squared plus B squared equals C squared over here on this triangle that we're working with, I don't know what B is, right? I'll call it B. But I do know that 3 squared plus B squared must equal 5 squared, right? That's using this. And then let me just see what that is. That's 9 plus B squared equals 25. I will subtract 9 from both sides, so b squared is 16. And then I take the square root on both sides. I get plus or minus 4. Now be careful, because when you take the square root on both sides, you have to do plus or minus. But I'm going to throw away the negative. And the reason I'm going to throw away the negative is because obviously b is the side of a triangle, which means that it has to be positive. So we're going to put 4 here. Yay or nay?
Yes, sir. So now that we have all the sides, we just plug it in.
Just plug in. Yep.
Okay.
So let's do sine. Sine is opposite over hypotenuse, so that's just the opposite side is 4, so that's just 4/5, right? Cosine is adjacent over hypotenuse, so Jordan there?
I'm here.
Okay. I was going to ask you for cosine.
3/5.
3/5, so that's the adjacent. Okay. Jackson, what's tangent?
It's going to be 4/3.
So that's opposite, right? Opposite over adjacent. So we're doing this 4/3. Good. Okay, good. Yamna?
Yes, sir.
Yes, what is cosecant of this theta?
Is it 5/4?
Yeah, so it's just the sine one flipped. Okay, so it's just that one flipped, 5/4. And all of the rest of these are just the others flipped, right? Cosine is the, secant is the reciprocal, so I just flip it, 5/3. And then for tangent, I flip it over. For cotangent, I get 3/4. Now, we could actually get on our calculator and like write those as decimals, but we're going to leave them as fractions. That's our answer. It's just a ratio. Is that clear?
Yes, sir. Also, wouldn't it be easy for these to get them in decimal form, like if we had to?
Yeah, that's what I'm saying. You can do like 4 divided by 5 on your calculator, come out to be 0.8, and then so on and so forth.
Okay.
And later on, most of our answers are going to be decimals anyway, but yeah. Okay, let's see something, some other identities. So like I said here, cosecant is basically sine flipped over, which means that cosecant of theta is the reciprocal of sine. It's equal to 1/sine. So it's just flipped. And then secant is 1/cosine and cotangent is 1/tangent. So these are identities. These are in your formulas, but I'm just putting them down here. And then there's these two identities, which I think are very useful, especially in calculus, is just remembering that tangent of theta is really just sine theta over cosine theta. Why is that true? Okay, so let's see. Tangent is TOA, right? SOHCAHTOA, right? So tangent of theta is opposite over adjacent. That's what it is, right? But what's sine? Sine is SOHCAH, so
Opposite over hypotenuse.
Hypotenuse. Okay, what if we took that and divided that by cosine theta? That's adjacent over hypotenuse, isn't it? And what would happen is the hypotenuse would cancel and you would get opposite over adjacent, which is the same as tangent. So I'm just trying to get you to see that this is true. The tangent of theta is just the sine of the angle over cosine. And then cotangent is just flipped over. All right, here we go. If sine of theta is √3/2 and cosine of theta is 1/2, find the value of the other 4 trig functions. Okay, so we need sine, cosine, tangent, cosecant, secant, and cotangent. So let's start with the first one we don't know. How about tangent theta? So tangent theta, by definition, is sine theta over cosine theta. But sine theta is given to us, isn't it? It's √3/2 over cosine theta, which is given to us, 1/2. And just so we're clear that what's happening here, division becomes multiplication of the reciprocal. The 2's vanish away and I get √3. Questions? Next one. Let's do cosecant theta. In cosecant, Genesis, you there?
Yes.
Genesis, cosecant is the reciprocal of what? Which one? It's either what one, it's one of two. Do you know that part? It's one of two. It's either sine or cosine? Or no?
I'm not sure.
Okay, so look everyone right here. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine, and then cotangent is the reciprocal of tangent. So this here should be the reciprocal of sine. Genesis, what was sine of the angle? What was sine of theta?
Square root of 3/2.
Okay, so cosecant should just be the reciprocal of that, which is just it flipped, right? So what should it be, Genesis?
2/√3.
2 over the square root of 3. Okay, now we've come to a point right now that I get very unhappy about. All right, this makes me very unhappy because the book is going to want you to now do something to this answer. They're not going to want you to leave the answer this way. They're going to want you to do something. Does anyone know what it's called? What we have to do to this?
You have
Don't
to
you
rationalize it.
Yeah.
Yeah, it's called rationalizing the denominator. Y'all heard that before? So I'm going to go to a new page because I don't like this so much. I don't even want to put it on that paper. Okay, so this is our answer right now, right? What the book wants you to do is this. They want you to take this and multiply the top and bottom by the square root of 3. That's called rationalizing the denominator. And what happens is on the top, you get 2 times square root of 3, but on the bottom, when you multiply these two together, the root goes away and you just get 3. That's called rationalizing the denominator. So I know some of you already knew to do this. Why do we have to do this? Or do we have to do this? Who told you you have to do this?
I don't think you have to. It just looks pretty, right?
Looks prettier?
When you have
I don't know.
a square root.
I would
at
argue
the
that
bottom.
I don't
argue
think
that
it
that was
does, but
prettier
it
than
makes the
this.
denominator look better.
It makes the denominator look better, right? But
When you have a square root in the denominator, it's an irrational number, isn't it?
it doesn't have to be. And you know what? Even when the root goes to the top, it would still be irrational. So I'm going to tell you why, okay? And this is why I get so upset about this. I was told, just like many of you, that you can never leave your answer like this. That's what I was taught also, all right? But I guarantee you right now that if you get on your calculator and you type this in, I'm going to do it right now. If I take 2 and divide it by the square root of 3, I get an answer. It's about 1.1547. And if I do the other one on my calculator, I guarantee you're going to get the same answer. Okay, so they are the same exact number. We're not doing anything because multiplying by this is multiplying by 1, and that doesn't change the answer. It just looks different. So it bothered me for a long time. Why does that have to be switched? And I'm going to tell you why. And then you're going to be pissed off like I am. Okay, so imagine a day before calculators. Okay, can you imagine that day? There are people still alive that grew up doing math without calculators, all right? So because math has a lot of weird numbers in it, and there were no calculators, no computers, these numbers, people had to just memorize, okay? So like, for example, pi, people just had to know that that's approximately 3.1415, and it keeps going on forever and never repeats. And they actually had competitions of like, who knows pi out the furthest? Like, oh, you know, I know pi out 30 digits. How many do you know it? You know, and then, well, I know 50, you know, it was like this kind of like, I don't know, kind of ridiculous, but that's the way it was back then. I actually have a colleague that I work with that still is in the math department. that claims that he knew pi out 120 digits, and I have witnessed him go out 60 digits. So he has verbally just spit out 60 digits correctly to me. So I believe him. And I think the world record for it is 16,000 digits. Someone knew it. Anyway, okay, whatever. So you would have to memorize these things. Square root of 2 comes up a lot in math. So you'd have to know that that's 1.414, okay? And then there's other numbers like E is approximately 2.718. So imagine no calculator, you're having to do math and you've got to know these numbers, have them memorized, right? And let's say you get to a problem and you're working on this problem and you get this expression, 1/√2, okay? That's where you are, that's your answer, but you're trying to get the decimal answer of this, no calculator. Well, how would you do this? You would go to your old school division, right? Just like if you want to take 12 and divide it by 3, you would do 12 here and 3 here, right? That's what you would do, the old school long division. So let's try that with this. So inside the division box, I'm going to put 1. And outside the division box, I'm going to put √2, which I have memorized because I don't have a calculator. And that's going to be 1.414. And then just like you would do here, when you're looking at this, you say like, what do I multiply 3 by to get 12, right? Here you have to say, what do I multiply 1.414 by to get 1? And it doesn't go into 1, so you'll have to add a decimal and a 0. And now you ask yourself, how many times does 1.414 go into 10? So how many times does 1.414 go into 10? You can't use a calculator, right? That seems a little bit troublesome, a little bit, yeah? Okay, so let's do this. Instead of doing that, let's rationalize it. Let's multiply by √2/√2. Okay, let's do that. And let's see what happens. Well, all that happens is the top becomes √2 and the bottom becomes 2, right? You all see that? But now do the division. What goes inside the box?
Square root of 2.
The √2, which you have memorized, right? 1.414. And what goes outside? A nice number, right? 2. Now, does 2 go into 1? No. So then I put a decimal. Does 2 go into 14? Yes, 7 times. And then I can start working this out and I get 0.707. Much easier to do by hand. Do y'all see that? Much easier. Now, if you did this one by hand, you would still get the same answer, 0.707. Okay, you would still get the same answer. But the arithmetic, the actual mechanical process with paper and pencil is so much easier to do here if you don't have a calculator. And so it became like a rule back then of you must rationalize your denominators in order to be able to succeed in getting the answer. And somehow it has just stuck in our education system. It's completely unnecessary. All right. So your book is going to want the answer rationalized, but on a test, I don't care. In fact, I kind of prefer when you don't, because it's kind of like a, middle finger to everyone saying, you know what I'm saying? Kind of like, why are you teaching me this way? This is like archaic. I don't need to do that. Why are you telling me to do it? I don't like it when people teach people things just because they were taught that and they never thought about why. Doesn't that bother you? It bothers me. Okay. Now, man, I'm all over the place today. It's all right. It's Friday, right? Kind of Friday. Last day of the week for us, right? Okay, so I'm going to rationalize it just because I want you to be able to get the same answer on the computer. I'm pretty sure the computer is going to count it wrong if you don't. All right, so that's what cosecant is. Now, what is secant? Secant theta is going to be the reciprocal of cosine. That one's easier, right? Because cosine was 1/2. So secant is flip that over. You get 2/1. That's just 2. No rationalizing to worry about. What are we missing? Cotangent, right? Cotangent. So cotangent theta I have two ways of doing this. I can do cosine over sine, or what's easier?
Do 1 over tan.
Yeah, it's the reciprocal of tangent, right? So if tangent is the square root of 3, which is same as square root of 3 over 1, then I can just flip that over and it becomes 1 over root 3.
And that would be our answer, right? Just 1 over 3 or 1 over square root of 3.
That would be the answer I would be happy with, but that's not the answer the computer is going to want. They're going to want you to rationalize that. And we're going to very gritting our teeth, we're going to do it, okay? Multiply the top one.
So on our exams, if we got like 1 over square root of 3, we could leave it like that.
You could, but I would definitely do it because as you're going to see as we progress through this course, a lot of things, they simplify and they rationalize. So if you want to be able to recognize things later, you're going to have it rationalized.
Oh, okay. So just like keep it.
Just
one
get
way
used to it.
anything.
Yeah,
Okay.
just get used to it, unfortunately. Okay, we have answered the question. Just one more little side note here. The way that I remember that cosecant is the reciprocal of sine and not cosine, and this is just the way my brain works. I just look, there's an S in there. So it's the one that's the reciprocal of sine. I don't know why my brain does it that way, but that's the way I remember it. And then secant, I don't know, it doesn't have an S in the middle, so it must be cosine. I have no better guidance for you. I'm sorry. You're just gonna have to remember it. I know that makes no sense, but my brain doesn't make a lot of sense sometimes. Okay, Pythagorean identities. So the Pythagorean identities, not the Pythagorean theorem, which was a squared plus b squared equals c squared, right? That's the Pythagorean theorem. The Pythagorean identities are these three identities. And I cannot begin to tell you how important this one is, all right? This is going to be used. You're gonna see that all over the place, all right? Sine squared of an angle plus cosine squared of that angle is always equal to 1. And I'm going to add something to this. I want everyone to be aware that when you write this notation, sine squared theta, what it really means is sine of theta, whatever that is, squared plus cosine of theta, whatever that is, squared plus 1. So what I'm trying to get you to see is this notation of putting that 2 right there means you're squaring the sine function. You are not squaring the theta, you're squaring the sine function itself. So if I were to write, let's say, sine with a 3 here, theta, that would mean sine theta cubed, right? This is just a side little note here. Now, we can actually prove this is true. We can prove this is true pretty easily, actually, to prove that this identity is true. Do I want to see it proved, or do you just want to take the formula on faith? I don't care.
Prove it.
Sure. It's not hard. It's just something that it's going to take a little bit of time. So, all right. So all we do is this: we take this and we take the Pythagorean theorem. A squared plus b squared equals c squared, right? We just take that. Very simple next step, but it's not something you would just naturally think to do. I'm just going to divide everything by c squared. Okay, I can do that because it's an equation. I can divide both sides by anything I want other than 0. Y'all agree with that? Okay, now this is equal to 1 on the right side. And then notice on the left side, that is the same as a over c squared. And this one is actually b over c squared. Yes? But if you look at your right triangle, a over c, right? What is a over c? A over c is adjacent over hypotenuse, isn't it? That's adjacent over hypotenuse. And what's adjacent over hypotenuse?
Sine.
Careful. SOHCAHTOA.
It's cosine.
Cosine.
SOHCAHTOA. So the A divided by C is the adjacent over the hypotenuse, which is cosine. So this is cosine of the angle squared plus, now this one, B over C, opposite over hypotenuse, which is sine. So this is sine of theta squared equals 1. Now, the formula has it the other way around, right? It has the sine before the cosine, but it's addition. So it doesn't matter what order you go in, right? Addition can be moved around. So that gives us this formula. So do y'all believe it's true?
Yes.
Okay. Now
I
the
have a
other,
question.
yes,
So if you put the theta at a different angle, wouldn't that switch around which ones were opposite and which ones were adjacent?
absolutely. Absolutely. So if I had done, let's say theta here, right? Then yeah, what is opposite and adjacent changes. It would definitely change.
Theta would only be in one of those two
That's right.
corners.
Yeah, it can only be, yeah, because this is the right triangle, right? So it would have to be there or here, one or the other. Yeah? Okay. All right, so now the next formula is actually, you can get this one by just taking this formula and doing something to that. Yeah, I can do it that way. So let me show you real quick how to get this formula. Take the one that we just proved. Okay, and then what I'm going to do is just out of nowhere, I'm going to divide everything by cosine squared. Theta. And this becomes a 1 because cosine squared theta over cosine squared theta is 1. Plus, let's see, equals over here. This is 1 over cosine squared. But what's 1 over cosine? What's 1 over cosine theta?
Secant of theta.
That's secant theta, but then squared. So this is just secant squared theta. And then over here, sine theta, sine squared theta over cosine squared theta. Well, what's sine over cosine? What's sine theta? Tangent, right? So this is going to be tangent squared theta. And that's that one. Do y'all see that? Tangent squared theta plus 1 is secant squared theta. And then to get the last one, to get this one, we start again with that. We start again with the top one. Sine squared theta plus cosine squared theta equals 1. And we divide this time by sine squared theta. On both sides. And if you do sine squared over sine squared, you get 1. If you do cosine squared theta over sine squared theta, you get cotangent theta. And if you do 1 over sine squared theta, you get cosecant squared theta. So I won't work that out anymore, but hopefully you see that you can get this formula from that one. The one that I start up here, and I'm going to circle, that's the one you need to memorize. The other two, you need to know they exist. And if you memorize them, great. But that first one, you absolutely need to memorize. All right. And the sooner you remember these, the better for you. Okay. We have like 5 minutes left. And we did not get as far at all as I thought we would. But it's okay. I'd rather go slower as long as we understand what we're doing. Let me take a quick look at the assignment that we have for this. Because
so you want us to go back and finish the other 6 problems?
Yeah, you should go finish up 7-1 now. But the 7-2 homework, I'm gonna have you let me see here. For 7-2, man, I don't know how far we can get here. Nope. Yeah, so you can go do the first 6. That's it though. I think at that point, you'll probably get jammed up a little bit. So try and do the first 6 problems out of the homework. And you know what, let me try and do something. Like I said, it's my first time working with this. I need to adjust. No, I'll adjust the due date. That's what I'm going to do. So what I'm going to do, let's see here. So 7-1, going to edit this. Hopefully this lets me change the due date real quick. Here we go. So I'm going to make 7-1. It was due last night, right? I'm just going to make that due on Sunday night. Okay. So you can do it during Super Bowl. And then the right triangle, since we're not going to be able to finish it, I'm going to change that one. Instead of to Sunday night, I'm going to change it to next Tuesday night. Because I already know we're not going to be able to get, you won't be able to do all of it. So my recommendation for the weekend is to finish 7-1 and do the first 6 problems of 7-2. All right, do those. All right, that's pretty much it. I don't have any time to really get into anything else. Any questions?
No, sir.
No,
Thank
sir.
you.
Thank you.
Okay, sorry it took so much time in the beginning. I really, you know, that whole thing with the counting your way around the circle, I can't even find it now. But that whole thing of where we went around the circle, this thing, to me, that's worth the time we invested into it, because later on, this will just continually be there. And if you don't get it, then your chances of surviving this class are going to be limited, you know, reduced significantly. So we'll get back on track at some point. Have a great weekend, everyone. Be safe.
Thank you.
Fun. See you on
Thank you.
Monday. All right.
Thank you.
Thank you, sir. Bye.
Bye-bye. Does anyone have a question or anything? Do I need to hang out or are we good? No.